This film is part of the assessment of the Advanced Building Performance Modeling module. The film is covering our research topic entitled Simulation Study of Natural Ventilation in Two Cities. In this film, we will take you through our research journey on comparison of natural ventilation in the two cities of Dubai and London. The film will show how natural ventilation concepts in buildings were developed in the world, with a particular focus on Dubai and London. In this research, we will use the house of two floors as a case study example, and will simulate some futuristic design and orientation both in Dubai and London. Then we'll compare and recommend scenarios that maximize the positive and efficient impact of natural ventilation. The main aim of this research is to simulate and compare natural ventilation in two cities, and to show how natural ventilation process can differ from one city to another that have different weather characteristics. Furthermore, the research also aims to provide a preview about the climate studies in Dubai and London and how these affect the natural ventilation of the sustainable architecture. The research finally aims to provide a clear understanding on wind catchers in Dubai and London. The methodology relies on applying the IES software to simulate the proposed natural ventilation for a two-floor house in both Dubai and London conditions. The results will be produced as well as compared between Dubai and London. In the concluding section of the paper, some recommendations and suggestions for future research will be given. Dubai is a region where there is a typical desert climate throughout most of the year. In the months when the temperature is normal, the natural ventilation is possible. In Dubai's hot days, natural ventilation have the potential to maintain a favorable environment throughout the season. Natural ventilation is unable to take place in summer region of Dubai because too much hot weather does not show any effect on thermal mass. Actually, ventilation in the winter season of Dubai helps in reduction of the cost and overuse of the year-round air conditioning in almost every home and office building. Summers in London often are little warmer than the winter, with average high of 22 Celsius temperature in summers. The weather still changes to windy air and even rainy days. Many of the newly built houses and buildings in London have adopted natural ventilation to keep up with the comfort climate in summer, and for such reason, the architects have adopted ventilated buildings because they may increase user satisfaction and well-being while reducing energy consumption due to heating, ventilation, and air conditioning systems. And as already said, the thermal conditions are quite average in London in summer season. There is as such no need for artificial heating. Therefore, in London, natural ventilation is of required importance. Wind towers were built in use for summers in Dubai and were removed when the winter season came. These towers were planted in a square type distribution. The original house in Bastakia in Dubai has 3 wind towers simulated in it and also has a potential to be adaptive to the comfort zones and meet the comfort criteria considering the wind tower design. This figure shows the wind catcher application in one of the buildings in London. The building belongs to Eddie and Stanhope School with wind catchers activated in its structure. Courtyards have been formed as typical component of houses and buildings since the first human civilization is born, such as the Indus Valley civilization and the Chinese civilizations. In Dubai, because of hot summer, many apartments and buildings have a common courtyard where natural ventilation is possible. This figure shows the Majlis courtyard at Bastakia in Dubai. This is a shared courtyard where people relax and have natural ventilation just near their residential building. Courtyards offer ventilation to provide fresh air passing through the building and create a cool environment. In London, there are many houses and apartments that have courtyard ventilation to improve the quality of life of people. After understanding the natural ventilation in sustainable architectures and reviewing the literature in the two cities, Dubai and London, let's move to the second part, which will include the methodology, results, analysis, conclusion, and recommendations. The project consists of 2-floor residential building. The figure shows the floor plan of the house. The residential building need to be located in any location in Dubai and in any location in London. The locations were chosen using Google Maps. The orientation need to be studied to fit the most efficient orientation. The minimum standard of building specification need to be applied. The building need to be rotated to the optimal orientation and compare the results in terms of outdoor ventilation while using flow design software. Some natural ventilation strategies are studied, such as wind catcher and opening such windows, location and sizes. Moreover, different scenarios are suggested and the results are compared between the two cities. This was done by switching off the air air conditioning in Dubai during the winter season and switching off the heating system in London during the summer season. This figure shows the location of the land chosen in Dubai near the sea with a plot size of 33 meter by 42 meter. And as shown in this Google map, the location in London was chosen to be similar to Dubai's site that was beside a water surface with a plot dimension of 33 meter by 42 meter. The following was taken into consideration in IES: the area, dimensions, site characteristics, site potential and limitations. Moreover, the minimum standard of building specification was applied. The main inputs for Dubai IES model includes the following. The IES was utilized to build simulation model of the two-floor house using Abu Dhabi International Airport climbing data. And the main inputs for London IES model include the following. The IES was utilized to build simulation model of the two-floor house using London climate data. The simulation results of Dubai showed that the total energy used throughout the year equal 154.38 megawatt-hour, where the cooling system was set on all around the year. Then the cooling system was set off in the following months from November to February. And after building the model of the two-floor houses using London climate data, it was found that the total energy used throughout the year equals 684.59 megawatt-hour, where the heating system was set on all around the year. Then the heating system was set off in the following months from June to August. Using IES, the model courtyard was directed toward all directions starting south, then west, north and east. The results were compared in terms of outdoor ventilation by using flow design software and the flow design in IES software. IES simulation for optimal orientation was done for both locations, including the following inputs. Using climate consultant data for Dubai, it was found that wind direction from northwest during the year with velocity that goes up to 10 meters per second, and wind direction from northwest and maximum velocity is 15 meters per second during November to February. This table shows the result summary for all options of courtyard orientations in Dubai, and the optimal orientation was direction of courtyard with the least total energy of 152.34 megawatt-hour. The following figure related to the best orientation in Dubai. Flow design software was also used to find the wind velocity. Using climate consultant data for Dubai, it was found that direction from south and southwest during the year with velocity that goes up to 16 meters per second. Direction from southwest and maximum velocity is 10 meters per second during May to August. This table shows the result summary for all options of courtyard orientation in London, and the optimal orientation was north direction of courtyard with the least total energy of 616.94 megawatt-hour. The following shows all graphs related to the optimal orientation option in London. Flow design software was also used to find the wind velocity in London. The scenarios of natural ventilation that were proposed for both Dubai and London are: 1. Wind catcher. 2. Location and size of the windows. Next, some proposed options for both scenarios will be analyzed in both locations. For the city of Dubai, in the first scenario, the optimal orientation option was chosen to be the base case for the first scenario. The wind catcher was added with different options of the opening. Then the results were found using IES software. Since total energy for all wind catcher options are the same and equal to 154.38 megawatt-hour, the main concern was the temperature of the rooms in all options. Therefore, a quick study of the base case option was done to check for the critical rooms. This table shows the highest temperature for all rooms during winter. It was found that the hall and dining room in the first floor has the highest temperature on 12th of November at 3:30 p.m. Thus, the mentioned date was selected to be the subject of internal ventilation enhancement between 3 p.m. and 4 p.m. at the hall and dining space at the first floor. This table shows the result summary for all options of opening in Windcatcher in Dubai, and the optimal option was southwest and northeast opening, with the temperature range of the hall and dining room between 13.55 to 31.15 degrees Celsius. The following shows all graphs related to the optimal Windcatcher scenario in Dubai. The optimal Windcatcher option was chosen to be the base case for the second scenario. The location and size of windows was changed in each option, then the results were found using IS software. This table shows result summary for the options in scenario 2, and the optimal option was 2 windows only, with maximum temperature of the hall and dining room to be 23 degrees Celsius, and the velocity range of air in the hall and dining room to be 0.08 to 0.19 meter per second. The following shows all graphs related to the optimal location and size of window scenario in Dubai. For the City of London, the optimal orientation option was chosen to be the base case for the first scenario. The Windcatcher was added with different options of the opening. Then the results were found using IS software. Since total energy for all Windcatcher options are the same and equal to 616.94 megawatt-hour, the main concern was the temperature of the room in all options. Therefore, a quick study of the base case option was done to check the critical rooms. This table shows the lowest temperature for all rooms during summer. It was found that the hall and dining room at the ground level has the lowest temperature on 26th of June at 5:30 p.m. Thus, the mentioned date was selected to be the subject of internal ventilation enhancement between 5 p.m. and 6 p.m. at the hall and dining space ground level. This table shows the result summary for all options of opening in Windcatcher in London, and the optimal option was opening from all sides, with the temperature range of the hall and dining room between 20.12 to 20.76 degrees Celsius. The following shows all graphs related to the optimal Windcatcher scenario in London. The optimal Windcatcher option was chosen to be the best case for the second scenario in London. The location and size of windows was changed in each option, then the results were found using IAS software. This table shows result summary for the options in scenario 2, and the optimal option was skylight, small windows with maximum temperature of the hall and dining room to be 10.69 degrees Celsius, and the velocity range of air in the hall and dining room to be 0.07 to 0.14 meter per second. The following shows all graphs related to the optimal location and size of windows scenario in London. This table shows a comparison between Dubai and London results. As a conclusion, while implementing the natural ventilation in houses and buildings, all the ventilation strategies must be taken into account, considering the climate change, flow of air, density, volume, and etc. It is noticed while simulating on IES that the swimming pool does not have any effect on the results. Also, it was found that the wind velocity when passing over the pool location has the same result if the pool was not present. Therefore, evaporation cooling using the pool was not valid, especially at the scale of the swimming pool. On the other hand, it was proven that natural ventilation plays a big role in reducing the energy consumption over the year. However, the energy consumption is still believed to be linked to the building envelope and isolation material used. Moreover, in London, skylight was needed in the windcatcher to capture the maximum amount of sunlight. Alternatively, in Dubai, orientation of windcatcher openings plays a vital role.